Okay, so here we go again. Second half of chapter 16 for AP Physics. Just a good general introduction into the concept of charges and fields. So chapter 16 going to be covering 7 and 8 basically, 16.7 through 16.8. So if you think about it, we've just finished up talking about charges and how we can determine the charges that exist between them. And I mean, not just the charges, the forces that exist between them. So if you had a positive charge and a positive charge on with the y-axis running through them, and maybe right here a positive charge right here, then we discovered that we could find the force by the principle of superposition, basically, and vector addition. We could find that this force is going to be pulled, or I'm sorry, let's see if I can grab that. No, I can't. And well, this one is going to be pushed here, and 3 is going to push on 2 this way, and then the summation of these two forces will give us the net force acting on 2 from 1 and 3. So now we're going to talk about how an electric field and we're going to can affect, or how they're created, and I don't know about created, but we can talk about the electric field that exists around a charge. So imagine if you had a charge just here in space, and it was positive. So first thing we want to do is just get some rules set up. So in general, this charge has field lines, and remember now, a field is a non-contact force, so it exerts force at a distance, action at a distance, if you want to call it that. And if I were to have made that a perfect circle, then all of these field lines would have come in at 90 degrees. Or if you were to put tangents to the circle, they would be perpendicular to the tangent. So these are all the field lines coming out. And basically, the more field lines you have, the stronger the charge. So if you had 2 charges, then you could relatively talk about them in terms of one of the charges, if it had 8 field lines around it, would be twice as much as another charge that had 4 field lines around it. So that's just a general idea there. So if you see the number of field lines, you can relate it to the strength of the charge. So what if there's a negative charge? So negative charges have field lines coming into them. Notice that they're touching the charge. Don't make your vectors, and incidentally, fields are vectors, so we can add them as such. But don't make your vectors stop before they get there, because that's showing that basically what that vector does is what your field is doing. So when you make it stop, then the field stops before it gets there, and that doesn't make any sense. So again, they're coming in at right angles. So what does it look like when you have a positive charge in the presence of a negative charge? So basically your field lines go out, and of course they want to be attracted to the positive, so they would come out and over and in. So notice going in, bad right angle there, but there you go. So you get the idea. Now I'm just going to put a couple on here, but it could get pretty messy, and the ones coming out of the back are going to go around and come in, and so I think you get the idea here. It's sort of weird looking. So, but here, let's just outline this area. There's a field, and so if we talk about that field that exists there, then that's what we want to talk about. So in this next slide, let's sort of look here. So if you put a charge, a small test charge, when I say small, think about if you wanted to measure gravity. So if you want to measure the gravitational field, so you take a small test mass and you would see how much gravity is pulling it down, and you would end up with a unit such as newtons per kilogram, and that would be the units of a gravitational field. Because if you took 1 kilogram mass and put it at the surface of the Earth, for instance, then you would measure 10 newtons per kilogram. And if you went further away from Earth, you'd get another measurement. But notice that this is a small mass, so that doesn't disrupt the gravitational field that you're trying to measure. So the same is going to be true in electric fields. So we're going to take a small test charge, which a lot of times is abbreviated as like Q test, and we're going to put it in the presence of a electric field, and they're going to measure the force exerted on it. So if you put this test charge in the presence of a positive field, so this is no longer part of the picture. Then we know the field lines emanate outward away from it radially, and then this little Q, and it's a small positive test charge. Sorry, I didn't mention that just a minute ago. So which way would that feel a force? Well, it would feel a force in this direction, to be pushed away. And so that small positive test charge is being pushed away, and you'd measure the force in newtons acting on it, and lo and behold, you've got newtons per, remember we measure Q in coulombs, newtons per coulomb. So we now have the electric field strength at that point in newtons per coulomb. So the electric field strength is, and then of course if we were to get rid of the units here, well, we don't never want to get rid of the units, but we would now have force per charge. So the short abbreviation is E equals F on Q, and again, it's commonly written as Q test in a way. Okay, so there's the electric field, and if we have it, and we can sort of define an electric field by putting a test charge in the presence of a field, and then seeing how much force is acting on it, just like we would do with gravity. Now, the interesting thing about electric fields, is that you can have fields that are attractive and repelling, whereas in gravity it's only attractive. So everything is attracted. Okay, so that's just a simple concept there. I think not too hard to understand that. And so now the other thing is how does the electric field change as a function of distance away? So what does the electric field look like from a single point charge? Again, these are abstract concepts in a way. A single point charge sitting in space, but it's still the math and theory are there, and it all works out, and these fields work wonders in terms of photocopying machines and just other aspects of like I said, cleaning the air and the smokestacks. But we'll get to that more discussion in class. So here's your field, and I mean this of course has a field around it that's going out into space. Remember, radially away, and let's just say that we put a particle, a little or nothing right there, and we want to know what the strength is of this field from that point. Well, then again, this is a pretty simple equation. You're not responsible for deriving it or anything. You're just responsible for using it. And if we want to know the electric field strength at that point right there, or maybe this point right here, or this point way up here, so these three different points, then we would just merely need to know the distance there between the 2 points, and we'd use this general equation. E, the electric field strength at a given point, is equal to K, Coulomb's constant, you remember that from Coulomb's law, times the Q, which this Q is the one that I'm talking about here, because there is no charge and there's nothing at these 3 points, over R squared. So it's actually not that hard to derive it if you want, using E equals F on Q and Coulomb's law. You can. I'll let you sort of think about that, see if you can come up with that idea. And F between particles equals K Q1 Q2 over R squared. So by doing a little bit of substitution, you can get to the idea, and I think you can see how you do that. So anyway, this equation tells you, very important, because we're going to get a lot of equations here in these next couple chapters that look for sort of similar, like electric potential, A equals KQ over R. Don't worry about writing that down right now. But we're going to get a lot of equations that can look similar, and I want you to know what they are. So this one is electric field strength at a given point. So if we wanted it from here or here, we just need to know that distance, and here we would just need to know that distance R between the 2 point, the point in question and the actual charge. And remember, this is the strength of the charge. That is that strength of that charge. So that's the general idea. One last thing I was just going to mention about fields is, if you think about it, going back to the slide, then what happens to an electric field if this q all stays constant, then you generally have a simple equation is that it follows that 1 over the square of the distance, or it's an inverse square law, so 1 over r squared. That's if k stays the same, and of course it does, and q stays the same. So if you double the distance, the field becomes 1/4 as strong. Triple, 9 times less. Quadruple, 16 times less. You get the idea. So let's wrap up here with one last concept here, and then we'll do a quick review. So here we go. You had electric fields that existed between 2 points, but there's also this idea of electric fields that exist between parallel plates. So imagine if this plate was charged positive and this was charged negative. So you would, and this is a special case where you have an electric field that would run straight across like this. Again, notice that they're 90 degrees, and you get a little edge effect too, which is usually sometimes a little bit complicated. No, not that much, but it's sort of interesting to draw. So yeah, but anyway, within this part right here, which I'll just highlight, this area right in here, this is a uniform field. And all that means is that if you put a test charge in there, anywhere you put it in there, you would get back the same electric field strength, so the same newtons per coulomb. So you put a Q test here, or here, or here, they'd all have the same force because it is a uniform field. It does not diminish as a function of distance. So just a unique field, but that's something very simple to remember. What's nice about this is that you can actually start controlling which way like an electron would go if you shot it through up down at the bottom here. So and this sort of gets to the idea of like a cathode ray tube or something where you can sort of deflect electrons or protons for that matter, but mostly electrons. So anyway, we'll stop with that concept right there, and that'll be a simple way. So get those formulas down. You have 3 so far from this chapter. All right, that's it.